Today's sort of a start at the top and coast to the bottom kind of day. We're going to start with exponential random graphs, which will sort of blow our minds first thing in the morning. Then move on to a workshop of some material, some hands-on stuff. Then Giovanna at lunch is going to talk about RDS and network sampling of memory. And then at that point we'll all be exhausted, so I'm going to throw some eye candy about visualizations and how you might do that, introduce you to PAYEC. And then we'll end the day with experiments. And Manoj Mahan is going to come in and talk about an absolutely remarkable network intervention they're doing in India, which is nationwide. It's remarkable. So that's the scope for today. It's going to, I don't think it's quite the fire hose that yesterday was in terms of the breadth of topics, but then we might be going a little deeper than we had thus far. So okay. Jeff, the floor is yours, man.
Okay, very good. All right, so thank you. So today, the topic for the first 3 hours, as Jim has said, is exponential random graph models. This is going to basically take off from where we left off on yesterday, trying to figure out how we can statistically model a network, okay? And so I'm going to assume we sort of remember a little bit about what happened yesterday and go from there. So let me first just give you the macro structure of the session. I didn't have donuts in here, but there's going to be a 5-minute break for donuts. I could edit it, but I won't. I don't know. Okay, so this is a sort of 2 sessions. The first part, hour 15 minutes, is going to be mostly lectures and your questions and basically an overview of what do ergms look like? Why would you want to do this? What are all the problems? Why would you not want to do this? And like, I'm going to try to give you a sense of how to interpret the models and sort of what's the benefits, what's some of the costs, as well as some of the likely problems you're going to face. And you will face problems. That's just a warning. These models are incredibly finicky, and this is a sell job. You should use these.
Thanks, Jeff.
Yeah, no, they are really useful and really hard to actually get to work. And so take some care. And so that's, in some ways the first part is just to give you a sense of what it looks like, and the second part, the hands-on approach, is really the as I just said, it is hard to fit, and so I want to give basically a demonstration on exactly how hard it is to get these things to work, even on a single network. In a fairly simple model, simple models are okay, but complicated models, even on a single network, can be hard. And so we're going to go through, just walk through what I would do if I were modeling this network, and we're trying to get it to work. And so we want some sense of what it means to work in the first part, so that we know what success looks like. Okay. And so the timing, out 15 minutes, and then the second part, hour and a half or so. In the past, I've done this on a full day. It could be a full day if you wanted to, but I think we'll cover enough that you'll get a sense of what to do. And so in terms of the actual sort of second parts, the key would be fitting the model and being able to know if the model converged, and then being able to check model fit. Okay, so that's the plan. With that in mind, what are the goals? Well, get you a sense of what ergms are, what you can do with them, be able to fit it with your own data. In this case, we're going to use some ad health data in the second session, and then sort of really these sort of 2 things are sort of crucial. First, to understand, what does it look like if the model worked, in the sense that you have interpretable output or not, and then sort of a second related point. Is the model any good? So first, is the model, you can get it to converge, but the model could be terrible. If it didn't converge, it's almost certainly terrible, but these 2 things are theoretically distinct, and so we need to get a sense of what both of those look like. And so in the end, what should you be able to do after 3 hours? You should be ergm experts, obviously. That's no, you should be able to at least run the models in R, figure out sort of how to interpret it, and then know if there are any problems. Okay, so today, so the introduction. And so the first part, in terms of just why, more generally, why statistically model a network, we sort of started to think through these problems yesterday, the end of the day. I'm going to motivate it in the particular context of the exponential random graph models, but this will hopefully feel somewhat familiar. Okay, and then we'll get into some technical details, not Not too many. We have an hour and 15 minutes or so. So it's going to be sort of a high-level view of what these models are doing, but we'll get enough. There'll be formulas, and so something is happening. There we go. Just enough to get a sense of what's happening, and then we're going to go over some examples of sort of the possibilities of what one could do. Although, of course, we won't talk about all of them because there are quite a lot of what one could do, and obviously it's going to depend on your particular case. And we'll talk about estimation just a little, just so that we know when we get to the R part, why our models, or what it looks like when our models have gone horribly awry. Okay, this is preparing you for things going horribly awry. All right, so preliminaries. Obviously, we know what a network is. We're on day 4 of a social networks and health seminar, but I just want to kind of discuss at least the scope conditions of what we're going to discuss today. We're going to mostly focus on full network data, so we're assuming we have all the nodes and all the edges between them. It can be undirected or directed. In the actual R session, we're going to work on a directed network, okay? And so that's what we're basically assuming, but I want to just highlight, and this sort of tracks back to the discussion on Tuesday on ego network stuff, that you can estimate these models using ego network data. So even individually sampled ego network data, you can estimate these models on. You can't estimate all the parameters on them exactly, but you can estimate a lot of it. And this is increasingly quite easy, more easier than it used to be. And this is thanks entirely almost to Martina Morris and the work of Pavel Kravitsky. And so that is, we won't cover algorithms on ego networks, but definitely possible. And if that is the type of data you have and you want to fit these models, the tutorial on the StatNet website is excellent. And so highly recommend looking up that work and heading in that direction. Okay, so why specifically model a network? So I'm just going to go through this sort of quickly just to motivate why bother doing this. Okay, so one reason is that if we're trying to understand what networks look like, we know sort of intuitively that different contexts and different networks in different contexts may look a little different. This is just a sort of random sample of networks that I happen to have from my class that I taught. And here we go. I'm randomly sampling backwards and forwards. Look at that. Okay. So the point here is that network structure and what we look at, the visualizations, right? The features of the networks can look really different depending on what we're interested in, what type of context, what types of relations, and the like. And so one reason, not the only, we're gonna have a list of reasons in a second, but one reason to try to statistically model a network is to be able to try to figure out why is it that the network in, this is a school 39. This is I guess I don't know what this is, but it's look at that, it's a nice picture.
It's an example of a racially diverse and racially integrated school from AdHealth.
Is it AdHealth?
Yeah.
Aha, very good. Excellent to have an AdHealth expert in there.
Not that I have every school in AdHealth memorized.
Right. Apparently, school 39. So there we go. No. Good. So this is I think this is also a school network, and this is a collaboration. But the point is that the features look really different depending on specific context. And so one reason to model a network is to try to figure out why. What is the process or the underlying local tendencies that make one network look different than another? So with that sort of in the back of our heads, here's a good list of why bother statistically modeling a network, specifically with the exponential random graph framework in the back of our heads, where the overall, and we'll see what the actual model is doing in a second, but the goal of an exponential random graph model is to be able to actually put a model on the underlying processes that generated the network. So what types of tendencies do we see that make ties more or less likely? So in the end, we're basically going to be trying to predict the presence or absence of a tie. People who are similar in terms of smoking, that makes a tie more likely, things like that. And so one reason, so in terms of, with that in mind, why bother statistically modeling a network, both in the sense that the models will allow you to basically estimate what tendencies ended up generating a network, and the fact that the features of networks can be really different. Why do it? Well, and so this comes from Gary Robbins' paper 2007. It's quite good in terms of, a little old now, but quite good in terms of laying out the intuition for, why try to put a model on a network? Why try to actually predict ties as a function of local tendencies? Okay, so I'll run through this pretty quickly, and then we'll get into what this actually looks like. Okay, and so the first part, and this was basically highlighted yesterday, that the idea is we collect this data. We ask who are your friends. We have zeros and ones, ties, no ties, but there's a danger of treating those zeros and ones as concrete, absolute, the 0, 1 that has to be. It's always going to be a friendship. And in fact, of course, that we may not think that's really true. That there's actually some uncertainty about whether that one is really a one. And so there's some underlying stochastic process or some stochasticness, messiness around the data that we actually collect. And so one way of thinking of what the network data we actually get is rather than concrete zeros and ones, that they are in fact just the particular realization of some underlying process. Okay, and so a statistical model approach, specifically exponential random graph models, is one way of making that explicit. One way of recognizing that in fact our zeros and ones are, well, a little messy and a little bit stochastic, and we want to take that uncertainty into account. So that's one. Two, and this is going to be perhaps more important for most practitioners, is this idea of testing hypotheses, right? So this is often why we run statistical models. We're able to test hypotheses, and we also got a sense of that yesterday, of how one would go about testing a hypothesis about reciprocity or transitivity or levels of homophily and things like that. These are questions we could ask, and so an exponential random graph framework makes it really straightforward, as long as the models actually work, to answer questions and test hypotheses about the underlying structural features of the network, and specifically what types of processes and actually generating the networks that we solve. So for example, we could ask something like, okay, is the amount of cross-race contact less than expected by chance? And when we think of by chance, we got a sense of that, what that looked like, possibilities yesterday. Specifically, we can compare that to a network of given size, and we can say, okay, look, if we created a random network and we said of that size, would we have found more or less cross-race contact than we would in the observed network? And so this is a way of answering those types of questions. So two more. So third reason. And this is where we sort of move beyond what we did yesterday, where yesterday we could have compared the rate of homophily in our observed network to a random network of the same size and the same number of edges, right? And we could say, okay, look, it's more or less, generally more, but we could have done that yesterday using conditional uniform graph test or QAP or these types of things. So we sort of have a sense of what we could have done with part two. Here we start to move somewhat beyond that, in the sense that we could basically include multiple parameters in the model. So not just homophily, but we can include things like homophily, transitivity, reciprocity, all in the model together. So basically condition, right? Did we see this rate of homophily conditioned on the level of reciprocity? And so what is that? How is that useful? Well, that allows us to start to think about competing or potentially complementary hypotheses about what generated that network. And so that goes back to the idea that different contexts have different network features. We may want to know, okay, why is that? What is the underlying processes that generated that network, that made one network look different than another? Okay, and so example, well, we could ask, all right, what creates a strong group structure in terms of grade? Is it the actual, differences in terms of mixing by grade itself, the homophily feature, or is it something to do with transitivity, norms of reciprocity, and the like? And so we can ask, right, how much and to what extent transitivity compared to homophily, compared to reciprocity is important in generating, structures that look like this, compared to that, And the idea is that we can do this simultaneously. So we sort of move beyond these single hypotheses about the features of a network compared to chance, and we start to get into a much more complicated set of conditional statements. Well, the rate of homophily is this, given transitivity, number of edges, and the like. Okay, so you can see that in some ways it's a direct extension of what we've done, but it ends up being much more complicated because we're going to try to do these things all at once. Okay, and last, and this is sort of related to this idea that these models make it very nice, and this is a very direct extension of micro to macro. The idea, question?
Is this sort of like bivariate statistics compared to multivariate statistics? Where I go, okay, I had one tie during process, I can do that and look and see that's random chance, and in this case I can actually look at how they condition each other.
I'd say it's certainly one of the main reasons why you'd want to do this, because you could, so I would say it's not the only reason you would want to do this, but certainly one reason is the fact that you get this much more potentially complicated conditioning statement you can put in these things all at once. That would be a good analogy. So because we saw yesterday that you can do a single statistic. This allows you to do multiple things, controlling for the level of homophily, looking at transitivity rates. Exactly right. Okay. And so good. So micro macro link. The idea here is that we can try to figure out, okay, what local processes do in fact generate the features of the whole network. And so this relates to this question of how these things are competing or complementary. And this just makes it a very explicit way of figuring out what that actually looks like. And so this is one of these really hard theoretical problems in social sciences, and exponential random graph models in some ways have it built in from the beginning as a way of trying to figure out. If you know the level of homophily and level of the local tendencies towards transitivity, how does that aggregate up to create whole network features? And so that normally very difficult connection between micro and macro is, we'll call it tractable. I think tractable within these models. And so these are all good reasons why we may want to do this. Okay, so let me just give you a couple examples of health-related questions, as it is a seminar on social networks and health. Then we'll get into some actual, the actual details of the model, and then we'll see, how these things work and how they don't work. Okay, and you let me know if there are donuts, and then we'll stop. We'll stop talking about exponential random graph models and do something more important. Okay. Anyway, so possible questions, right? And this is basically foreshadowing the kinds of things we're going to look at in the actual R session, right? We could ask things like, are popular adolescents more likely to drink, smoke, etc.? Of course, we could have asked that question without running an exponential random graph model. The advantage here is you can ask this question while conditioning on all kinds of other features, like the level of homophily on other characteristics, like transitivity, like norms of reciprocity, and the like. And so you can begin to ask, okay, net of all these other terms, is it the fact that high-status adolescents tend to drink, smoke, etc.? Okay. Second example, are people who smoke, drink, etc. More likely to be friends with other people who smoke, drink, and the like? Okay, so a homophily question. So this is essentially a question of, in degree. Do people who smoke have higher in degree? This is a question of homophily, but again, we can ask this question while conditioning on all these other types of features. And so here we go. How much of this tendency for people to befriend people who smoke, other people who have similar characteristics, how much of this tendency is in fact simply due to transitive closure and reciprocity? So this is the type of question which is very natural in the exponential random graph framework, and I would say, more difficult using other types of things. Maybe it's possible, but you kind of have to wrangle into making it happen. Well, this is a very natural type of question you can ask in this framework. Okay, So other things we can ask, right? Of course, we can ask about health advice and things like that. You saw yesterday questions of diffusion and epidemics and things like that. Hiding under the hood. So did you do epi model yesterday? Yes. Okay, good. So hiding under the hood of that is a exponential random graph model. They're estimating things, and then they're going to run diffusion curves over it. And so it's sort of hiding under the details there, but it is there, and so it is useful in trying to understand what epidemics are possible, what is the potential. And this goes back to what we had discussed on Tuesday on ego network data, that you can take ego networks and stuff, estimate what the network features would look like, infer it, and then you can say, okay, what would that look like in terms of epidemic potential, as well as, on the good side, our interventions more or less likely. We won't really talk about this, but I do want you to know that this is certainly one thing that is quite useful for. Okay, word of warning, too many W's. Okay, so the first word of warning. Wow, I'm going to change that slide title. That's terrible. Okay, all right. So the first thing, this is a finicky model, and in some ways, it looks like a fancy network model. Can we just measure it more simply? Maybe. The point is, if it answers your question, you should use it, and if it doesn't, don't use it. I don't know. And so, it's not going to make the paper more interesting. It is not an excuse for, not a substitute, I guess, for answering really good, interesting questions, which is obvious, but I put it out there anyway. And second, in terms of the technical details, how much of this, the technical details that you need to know in order to run the models. Surprisingly little, right? You can, of course, type in ergo and your model, and it will run, probably. We'll see. Fingers crossed for the second half of this talk. But, there's this tension between, of course, being able to run it and then, okay, understanding what happened. I would say the crucial bits are being able to interpret it, the output, right? Know if the model fit is any good, and knowing if the model has converged, so you can trust the estimates. There's going to be lots of technical details that we're actually not going to talk about, and I would say you really don't need to know that much to actually be able to interpret it, but you do need to know at least enough to say whether or not the models are any good. Okay, so good. Words of warning. So into model details. So let me pause there and see, are there any questions or any questions before we get into, look at that as a formula and everything, before we get into actual technical details and try to understand what the model is doing, are there questions or concerns? Okay, very good. So let me introduce what it actually looks like, and then we're going to basically just walk through what the model is going to do, what you can do with it, and the like. And so what I'm going to do is, so here's one version of how to write down the model. It may look a little different in other papers, but it's one version of it. I'm going to basically just walk through each piece. And so let me give you a general overview, and just we're going to walk through each part of it so that we understand what it looks like. Okay. So what's happening? Well, the basic idea is a lot of words here, but what's really important is that what you're basically trying to do is to predict the network itself, in the sense of you are taking all ij pairs in the network, and you're going to basically put a model on whether or not a tie is likely or unlikely, so the presence or absence of a tie, as a function of, so is there a tie between all ij pairs? This is the x part over here, as a function of, so the theta, these are coefficients in a traditional sort of logistic sense, okay? And then these zx's are counts of structural tendencies that we think are important in predicting ties between our cases, or ij pairs, okay? And so let me walk through each piece of that. but let me just give you, before I do that, let me just give you a sense of what's going to end up happening is, imagine you're trying to predict friendship in a high school. You're going to predict whether there's the presence or absence of a tie. It's going to be a function of, let's imagine, the structural tendency of interest is, let's say, is homophily on grade, and then you're going to put in a term that's going to say, is there match or not match on grade? It's going to count up the number of edges in the observed network that match, and then basically the coefficients are going to tell you whether or not that level of homophily is more or less than we expect in a random network of that size, given all the other terms in the model. And that's why it becomes complicated, is that it's given all the other stuff in the model, as we'll see. But okay, so let me walk through it. This is so the so the bold doesn't come out very well, but that is supposed to be a matrix. All IJ pairs. The bold in PowerPoint, ridiculous. But okay, so what's going on? This is our, if you want to think about this as in the simplest case, as a logistic regression, right? Our dependent variable in the language. So I teach the grad students, and so it takes a long time to figure out what the dependent variable is in any given case. In this case, we can think of it as all IJ pairs in the network. We're trying to predict, basically what I said before, whether or not there's the presence or absence of a tie. Okay, and so this goes back to this idea that we're not going to treat the zeros and the ones as the absolute concrete zeros and ones that exist, but in fact they're probabilistic, and there's some underlying tendency for these two people to be tied, and so that's what we're interested in doing, is trying to predict whether or not there's likely to be a tie between I and J, and we're doing this, of course, within a model, and so it is probabilistic. And so that is the outcome of interest. Is there going to be a presence or absence of a tie between all pairs of nodes, or all IJ pairs, is why it ends up being the network as a whole, because it's all IJ pairs at once. Okay? And so that is the outcome of interest. The other part, the thetas and the zx, what we're actually going to use to predict whether or not there is a tie, or likely to be a tie, between all of our IJ pairs simultaneously. And so for now, let's not focus on the thetas, focus on this zx part of the term. Okay, so what's going on there? Basically, what's important is these are actually counts. These are actually counts. These are counts of the different types of structural tendencies we may think are important in terms of predicting ties. And so we're going to go through lots of possible terms we could include. We're going to go through models of different versions of things you could include, but I want to give you, a sense of what's possible. You could, of course, count the number of edges in the network. You could count the number of triangles. We'll see what that looks like in a second. Homophily terms and the like. And so what this ends up actually being is these zx's are the counts in the actual network that you have. Okay, so you may count the number of edges, or the number of edges that have the same characteristic on gender, grade, race, and the like. Okay, so here's a little example of what that looks like. Imagine this was our little toy example network. I wouldn't run an ergom on this, but I guess you could. We have let's say 6 actors, right? And so let's imagine this is what it looks like. And if we wanted to think about what the independent variables are, or what the things you put in the model to predict whether or not there's a tie, they are the counts of the different types of things, different types of structural tendencies. And so, for example, imagine we wanted to predict whether or not there's a tie between all IJ pairs, and we're going to put in a term for edges. We would basically count up, right? This is what ergom's doing on the hood. It's counting up the number of edges in the observed network. Obviously, here we have 6. Okay, so I've counted them out from each IJ. In this case, it's an undirected network, so it's easy, but you can see, just counted it. Well, of course, we could do things that are more complicated. We have the number of triangles, right? So I don't know why that blue, but where I is friends of J, J is friends of K, K is friends of J. How many of those types of features we have, right? In this case, we have 2, right? And so, what's the point of all this counting, right? Well, the idea here is that we're going to ask, okay, are the counts, right? Are the numbers of these types of features that we get, like edges, like triangles, like, tell me these types of little counts that we get, are the counts of those types of structural features more or less than we would expect, again, this idea of by chance, a random network of the size of the Q node. So we're going to ask, do we see more triangles than we expect? Do we see more edges than we expect of a network of that size? And so that becomes the question, very similar to what we ended up doing at the end of the day yesterday. Here we're just putting on a more complicated set of conditions. So is the number of triangles that we see, well, they should never put triangles determined in the model. We'll see. As the number of triangles that we see, more or less than expect by chance, given the number of edges and other terms. So that's the idea. So we're going to take this next step in terms of asking the same question. Question, yeah.
Is that why we're using? Is that why it's an exponential function?
So.
The link between y, the more general point of like y graph is in an exponential family.
Yeah. So I mean, the simplest way to think about this is imagine you're running a simple logistic regression, right? It has the exponential form in order that it has nice properties. And so that's the simplest way to think about this, is that one thing you could do would be to string out all of your ij's, you have zeros and ones for each case, and you could run a logistic regression, right? Predicting a tie between I and j as a function of number in terms of whether or not the number of edges and all these types of things. And so you could think of this as a logistic regression where you're predicting the ties between them, and that takes the exponential form. And in very simple models, it is exactly that. That's all it is. So imagine so you strung out your ij's. It's a 0 or 1. It's a tie, and you just put an intercept term. That is going to be the same as running, throwing it into R, running an ergon, and putting an edges term in this. I mean, this is the same thing, right? And so, yeah, question? Multiple components. So, what do you? Are they not connected because there was no possibility of ties between them, or? Sure. I guess the question is it because they're in different schools and they never had a chance to interact, or is it because they just happen to they hate each other and they don't interact and oh my God, Okay. Okay. Yeah. So the answer is yes. You can do it. Imagine in the case of where there wasn't really a possibility of having a tie, you could basically put in structural zeros that says, basically a term that says this group and that group, the two clusters just have no chance of interacting. And so basically, yes, there are certainly ways of maneuvering around these things. So short answer is yes, but you would have to kind of think hard about how to do it.
I think the question is whether or not the number of components is a design feature of the network.
Right.
If it's a design feature, then you want to build the design into the model. If it's an empirical feature that just happens to be there are more components in school than another, then that's a realized feature that will show up in your network once you run the model. There's nothing about this model that predicts having a disconnection. There's no path for the statistic in the simplest of these models. Just to follow up on John's question, the original version of these models, which came out as P1, P2, P3, this is where these and later P stars were literally logit models. That's where these started. Turns out they have rotten estimation technique sort of properties when you do them as a simple logit, and this is what's generated this line.
Good. No, yeah, that's excellent. And I'll just add to the question in the back that one thing you could do if it was just a feature of the network is to estimate the model and then ask, is your model actually, if you simulated networks from the underlying model, does it replicate the number of components? Is it doing a good job of recreating these big divisions? And if not, then your model is doing not a very good job. And so in some ways, yes, it can certainly handle it, but the question is, can you create a model that faithfully reproduces the actual network? So good. Okay, excellent. I've gone backwards. All right. So counting. Okay, good. And so
Jeff, you want to point out a key point
yes.
back on your 2 stars there? So a lot of times these elements are known as configurations, and the configurations are not unlike the triad census where they're separate from each other. These can be nested. So there's a 2-star. There are many 2 stars surrounding E, for example. So there's BEA, BED, BEC. In the triangle BEA, you get one 2-star around B, another 2-star around A, another 2-star around E. And so these terms overlap a lot on the same edges. And whereas if we were doing a triad census, we would say that there's one triad here, ABE. We would remove the labels, and we would consider the ABE triad the same as the AED triad. And so that's a distinction about these models, and it's used as part of under the hood about the computation speed. But it's for those of us that think in logit models, this is what makes these models a little hard to fit, because essentially you have exceedingly high multicollinearity, right? And so so what you're trying to do is you have to have these estimation techniques to pull out the signal from a lot of multicollinearity in the data. So this is just an intuition, just trying to help you get a little intuition behind these configurations. So sorry to interrupt.
No, that's good. I would say, so on that note, you can, that's essentially an assumption, right? You're exactly right. So the models are making, as typically estimated, are making specific assumptions. And much of the assumptions are kind of hidden in the background, but some are not. And you basically, when you estimate the model and you decide what terms to put in and how to specify it, you are implicitly making an argument about 2 things. And this is, I think, often missed, I guess, that you are implicitly making a dependence assumption. And this is important, and we'll talk about this as we actually estimate things. And so dependence assumption in the sense of, okay, so if I'm interested in predicting, whether or not there's a presence of a tie between I and J, essentially what other things around IJ am I going to assume is affecting the probability of that tie existing? And so, for example, I may think that whether or not there's a tie from I to J is a function of whether or not J sends a tie back to I, right? So norms of reciprocity, in which case this IJ variable is dependent on what's going on from J to I, okay? So that's an argument, so it's a theoretical argument in terms of I'm going to put in a term for reciprocity, but it sort of in the background also making this argument about what is and is not dependent or what's independent when you're trying to predict a tie between I and J. Yes, question?
Clarify when we're talking about dependence assumptions, because I know this is something that I've struggled with.
Yeah, it's a hard concept, sure.
Right, so I know that some health network modelers recommend thinking about dependency in 4 specific steps. Where you have a null model, where you have a dyadic independence model, where you have a dyadic dependence model, and then when you have kind of higher order dependence assumptions.
Yeah.
Something, that's kind of more widespread, or is that something that's particular to this particular researcher?
No, I would say the developers of the folks who are writing the Argon package would generally agree that those are sort of and we'll go through something very similar in a bit. But so you're right that the intuition is the models get more complicated as you sort of veer farther and farther out in terms of, so imagine whether or not trying to predict a tie between I and J, it could be completely independent of everything going outside. It could be only dependent on what's going on within that diet, and we could range out, which we'll see in a second. And so, how far you range out just makes the models increasingly complicated. And so in general, yes, good advice to start simple and to build up. I would say that this is a pretty deep theoretical question that you need to answer. In your case, you want the simplest model that works. And so whether or not the IJ is dependent on what's going on 2 or 3 steps out is a substantive question. So there's no particular answer, but in terms of whether or not it's always going to be something you want to include. But you're definitely true that it goes from simple to complex. Yeah.
Have you seen any kind of models or any kind of results that, the network behavior, the structure of the question you're asking is, answerable with a simpler model like a dyadic independence model, or is it usually that,
Sure.
What we find because we're network scientists and we're interested in complexity is that those more complicated models with higher order dependencies are usually the best models.
Yeah, good. No, that's good.
Just to repeat the question for people in the back that might not hear, the question was, and let me make sure I'm getting it. The question is what kind of model do you need? And there's this notion of local, easy, sort of features that have very little dependence, like same race ties, same sex ties, something like this, where it's just a categorical feature or a degree feature, so people who have lots of ties, that's not dependent on what other people do, and so those are very simple local models. Or do you need really complex models, like the number of 4 cycles in the network, or the number of cliques greater than size 6 or something? And these end up being features that extend beyond ego and overlap in complex ways. And so the question is, how can we get good health behavior models using simple things only, or do we need to go on to these complicated things? And I think the answer is, it depends on the question.
Right.
Because, it might not be satisfying, but I think that's like I said. One thing to keep in mind is the simple features are necessary, right? So you have to have density, you usually have to have degree. These simple sort of features are the foundation on which these other more complicated dependencies rest. So you can't just throw in a model with triangles and not have density. That wouldn't make any sense.
Okay, lots of questions. Okay, and we're halfway through the time. No, that's fine. Okay.
I just have a question. If you're modeling multiple networks,
Dangerous,
for
but
example,
yes.
like the schools in Nepal,
Yeah, sure.
I said if you have like 60 networks, that there's no ties because they're
Mhm.
separate networks. Are the assumptions that you're building in about density or degree, are those specific to that network? Are those built into the model to be what you've seen across the sample of networks in your entire?
Yeah, that's a great question. So I guess the short answer is if you want to start comparing coefficients across the schools, right? So if you want to understand the strength of homophily on grade across why is it stronger in one school as compared to another, which we've done. You kind of want the models to be as similar as possible, but of course a alternative theoretical argument would be, in fact, the model itself is different across the schools, in which case, in some ways, that would be the substantive finding, right? That, in fact, this model that includes these terms, a simple model works here, but it doesn't work there. And so I think if you're specifically interested in comparing the strength of some particular, homophily on some term controlling for all these other things, it should be as comparable as possible. If you want to take a slightly more complicated view of literally the processes that generate the network are different across these schools, then it's a free-for-all, and you can run 60 different ergms, and I'll see you in a year or something. I don't know.
What you typically do, though, right, is you'd run the model separately on each setting, specify the model the same for each setting, and compare the coefficients in something like an HLM or a meta-analysis sort of framework. So you could meet this point of saying whether it's different in one school or another by saying I'm going to set that parameter, I'm going to fix the parameters to be 0 in one set or not, and then I'll let them move freely in another. So you could have nested specifications so long as they're to make it comparable in this meta-analysis sense. And there is some Gary Robbins has done a lot of work on these kinds of HLM versions of ergo. The key is, right to my knowledge, and Jeff, correct me, I've been up this in the last couple of years, is that you can't do it as a single mathematical equation the way we typically do in an HLM model in most health behavior stuff. It's currently you estimate the coefficient and then you re-estimate essentially a meta-analysis on those coefficients. Is that true?
Unless so you could try to stack them all. I don't know if I mean, it'd be complicated. You could try to allow some terms to vary across the school. It'd be complicated, but possible to try to do it all at once. I don't know if I'd want to do that. Yeah, I don't think it's practical, but I think it's theoretically possible. Yeah. Okay.
Okay, I'll go first. So the dependent variables, the ties, and the independent variables are these configurations.
The counts, yes.
So how do attributes of nodes
Ah,
into these models?
good. Okay, so imagine, so we could flip ahead. Well, maybe we'll just say, no, not too far. Where are we? Okay, so we flipped ahead, but yes. Okay, so the short answer is, so basically what I was so moving from simple to complex. We skipped the important point of interpreting the coefficients, but we'll circle around. Don't worry. Okay, so basically, imagine you wanted to ask a question like, do people who are smokers, do they receive more ties than non-smokers? This ends up basically being comparing the mean in degree, allowing basically mean degree to vary between the two groups. And so it's actually fairly straightforward in terms of adding nodal characteristics in terms of being able to compare. You're basically just comparing mean count of number of ties for this group compared to the mean count of ties for this group in degree. Does that make sense? Yeah. So
the basic idea, right, is that there's still counts, just like the other counts of triangles, but it's counts of the number of ties that whites receive compared to the number of ties that blacks receive, the number of ties that fall between a white and a Hispanic versus a Hispanic and an Asian. So these end up being counts on the dyad, just like you could have reciprocity as a count. So they just end up being counts that are based on the coloring of the nodes as opposed to the pattern of ties on the nodes.
Okay. And so does the same go for attributes as dependent variables? So just instead of the ties,
No,
we have.
that's something else entirely.
Okay.
Yeah. But key here is that the dependent variable is the network.
Okay.
Yeah.
Do these always need to be dummies?
dummies in terms of.
So for instance, if you were interested in income, you would need to operationalize it into low income, middle income, high income, and look at the tie set between. You couldn't have income as a continuous.
You could have continuous. There are terms for continuous. Yep, exactly. Yep. Mm-hmm.
There was a question far back. You can answer? Yeah.
I think I reviewed all the jargon a little bit. Struggling with the independence versus dependence assumptions. So this set of models is trying to basically get away from what is the conclusions where everything's chopped together and get methodologically together along into statistical inference.
Yes.
So that's where this model kind of sits in the wider options for models that can be used with network analysis.
Yeah, so it certainly allows you to range out farther in terms of the, it's not
Could you
just.
repeat the question? We couldn't hear it in front. I'm sorry.
Not sure if it was okay. I'm struggling a little bit with the assumptions around dependence versus independence. But I'm new to the language in this field, so I'm trying to understand this set of models, the ergo models, are trying to get more into statistical inference, right? And
Mhm.
get away from some of the issues around independence and dependency we're coming up against with logits for this kind of data.
So certainly part of the appeal is that you can put in terms that so essentially allow you to range farther out into the network. So it's not just that whether or not there's a tie between me and you is a function of whether you send a tie back to me, but it's also what's going on with other people that I may be tied with. So essentially that is the idea that my tie to Jim may affect the probability of me being tied to you or not. And so that type of idea that what's going on here may affect what's going on here is sort of easily, you can capture that fairly straightforward in these models. The other big appeal is that you can put in multiple things at once, multiple types of counts at once, so you can condition the edges conditioned on the level of reciprocity related to what's going on with transitivity and all these things at once. So it's both the idea that you can kind of range out farther and that you can condition in a pretty complicated way in order to ask questions, is the level of homophily on grade? What does that look like? Conditioned on all these other structural tendencies like reciprocity, like transitivity, and the like. Does that make sense?
I think so.
Okay.
Further questions, and then you can also have a demographic, right?
Yeah. Exactly. So do smokers, are they more popular controlling for, a host of other more structural features like reciprocity and things like that? Exactly right.
So it's more, you're considering it more specified than what I had done in the past. Is that right? Okay.
I would say so. I think that's a fair, I would say yes. Okay, good. Yeah, it's done.
One of the nice, so you can think of it as intuition. So imagine I care about whether or not, I care as a sociologist whether or not it's true that friends of friends are friends. And an economist might say, no, it's not, there's no interpersonal effect here. What's going on is that people make friends with the people they're close to, and I put a bunch of kids in small rooms, and they're close to them every day, so they form friends. So there's no actual interpersonal effect, would be the argument. In fact, there's just a propinquity effect. And so what we can do in the erg effects is say that we can disentangle those two. We can identify all pairs that share a room together, or share a ride together, or share some feature together, which if I just generated a model from that, would generate lots of closed triads, and ask, do I actually find more closed triads than I would expect, even after I've accounted for the fact that people are clustered in these settings and hang out together all the time. So this is the idea. This is what makes them so powerful, is that you can distinguish not just the dyadic sort of clustering features, these propinquity features, but you can also then ask, is it the case that we have this dependence on edges in these chain kind of ways?
Did you put that then into another model, this coefficient?
For something like behavior?
Yeah.
Yes, that's what a Siena model is doing, essentially. So that's what we do tomorrow. So today we're saying, let's figure out how we predict the model. Tomorrow we say, now we have all these models that predict the network, and we then use the network things to predict behavior in the two equation sort of framework. Sorry to jump in, Jeff.
No, it's great.
Related question. So how do you deal with the risk of type 2 errors because these features are highly correlated with each other? So in James' question, to be able to have these dyadic effects, proximity is it's going to be highly correlated, right? I'm in a small room, I'm going to have this, but I would disentangle it, and a sort of model uncertainty world, I don't want to kick out the possibility of these sort of farther ranging network features. So how does this model sort of handle that?
So you're worried with the fact that the
super correlated with each
the
other.
terms are dependent on each other, right? They're sort of
Right.
sub-counts of each other. Yeah.
Exactly.
Yeah, no, that's true, which is why they end up being hard to estimate in part. And so, in terms of sort of practical advice, I think this does go back to starting with simpler models and then building on. So starting with an edge term and then building on terms that build on that. So reciprocity and then perhaps homophily and then building on top of that terms that are going to then start to get into the GUESP and triangles and things like that. In which case, you begin to see how the coefficients are going to start shifting as we start adding terms that are going to be becoming increasingly collinear. And so I think that's so A, making sure that the model actually converges, and two, basically seeing how the models end up changing as we start adding terms that are in fact highly correlated. Of course, you can also look at the actual diagnostics that'll tell you how these things move together or not. I mean, it's also important just in terms of the interpretation, like when you actually look at the coefficients to interpret them in the sense that adding it, this ij, if you add that tie, then that's going to filter through both reciprocity and triangles and all these things.
Just one follow-up
Yeah,
question.
sure.
Quiet.
No,
So
that's good.
That probability term, I mean, is that a distribution of networks? So basically, like I have chances of, could I, like if I were to move this in a Bayesian sort of world, and I have that probability, could I have a distribution of probabilities, and I can see, for instance, how many, basically calculate an inclusion probability for each one of these dependent features?
Yeah, so I mean the model is certainly built, and we'll get to estimation very, very quickly. But yeah, so certainly the model is built on simulation itself. And so it's sort of a natural part of, it is probabilistic. You can take draws from the model, in which case, yes, on any given draw, you may or may not see a tie between a given pair. So yes, you're absolutely right. You can certainly do that. In fact, it's the most natural way of sort of presenting what's going on in terms of the model. So yes, that's absolutely the right intuition.
Exactly. At the end of the day, what this model is producing is for every square in your adjacent, every element of your adjacency matrix, you get a realized model-induced probability of a tie being at that set. And so that probability, that giant, your 0-1 matrix now becomes a continuous probability matrix with lots of different features built into it, and you can randomly draw from it. That's exactly what the NCMC chain and simulation things are doing at the end when it's working. Just to get back to your point about collinearity, there's a distinction between a model feature and a reality feature, right? And so some things are collinear by reality, and so the best, there's no model trick in the world that's going to allow you to pick out reciprocity in a sex network, right? Because sex is by definition reciprocal, right? So that's just part of the world. And so if you live in a world where managers live in one building and someone else lives in another building and they never interact with each other, then there's no model in the world that's going to fix that. And so the feature is that these models are trying to pull out a little bit of information from things where there's enough differences to it. But if your setting is such that there is no difference, then you're just stuck from the get-go.
Okay, very good. So let's let me just quickly highlight the other pieces of the model, and then about 20 minutes, or give or so. Is that about right? So about 20 minutes. Yeah. So I'll go into estimation and like what how many left. But okay. So the theta, the coefficients. This is often what we're actually interested in, right? And so what is it going to tell us? And so you can see here, the idea here is that the estimated parameters, which is ultimately one thing we certainly care about when we get the output, is going to tell us, right, whether or not we have a large or small, quote unquote, amount of that particular configuration, whether it's edges, triangles, homophily, what have you, relative, and this harkens back to what we talked about yesterday, relative to a random network of that size. And this is where we change, right, conditioned on all the rest of the terms. And so we may ask, okay, is the number of edges we see high or low compared to a random network of that size, given all the rest of the terms in the model? And so typically, right, we're going to see the parameter on edges negative. So what does a negative parameter mean? That means that there are less edges than we would expect in a random network of that size, which if we had just flipped a coin and it was even and the probability was 0.5 on each edge, right? And so the idea is that there are typically fewer edges than that, so we get negative terms. Positive terms would say, for example, on homophily, right, that the counts on the number of edges that were the same on grade are higher than we expect in a random network of that size with that composition conditioned on the rest of the model. And so these are on the coefficients are going to come in the log odds scale, because it has this exponential form. We could transform it, and we could calculate probabilities and the like, and that's how we're going to end up interpreting these coefficients when we actually get our output. And I'll go over when we actually run these in R. I'll give you a couple examples, but that's the basic idea. Does that make sense? Yeah, it's good, hopefully. Okay, if not, we will get more examples of this when we actually run it in R. Okay, and the last part, the normalizing constant, more on this later. Okay, good. No, okay.
That's just so we can have it be a probability, right?
Yeah, so you sort of need this in order to get the likelihood, in order to actually estimate what those coefficients are, and that ends up being really hard, which is why I went through it really fast. And there we go. It's done. If you flick through fast enough, you don't have to worry with it. That's well known. No, it's a joke. No, okay. Anyway, okay. So no. This is an important part of the model, and it is hard, and ends up structuring the way these models have to be estimated. And we will get to that very, very briefly in a few minutes. I'm not going to go through. So yeah, this could be a day lecture if you really wanted to. let me just highlight very quickly types of models we could run. And this basically it goes back to the question earlier about, well, what types of models are advised. So basically this is a rundown of possible things we could do from, as I say, simple to complex. So the very simplest thing we could do is just put in a term, has a lot of words here, but basically just put in a term for edges, right? We could do that. We could just say, okay, let's predict whether there's a tie or not based on the number of edges we see, and all other ties, everything else is, all ties are equally likely, and we're just basically going to flip a coin based on the observed density. Pretty easy. Basically, this is the equivalent of the things we did yesterday. But we could do it, of course. We could also do things that are more complicated, as we discussed already. We could add a term for reciprocity or mutual in the ergom language, mutual. And so now we, the I, whether there's a tie between I and j is now a function of what is going on for j to I in terms of norms of reciprocity. So we're sort of ranging out a little farther, okay? So right now, the dyads are still independent, but the edges are not, because I to j is dependent on what's going on between j and I. So within the dyad, right, they, what's going on is dependent on the other side of it. And so the edges are now dependent, but dyads are still independent. We could add more complicated things, right? These are just examples of types of models we could run. And this, so this basically is the same model. We have edges, we have mutual reciprocity, and we have now we would add in terms for in degree and out degree of each node. These models tend not to always work so well because they have lots of terms, but you could do it, right? You could put in terms for that as well. Perhaps more important, we could add in, as we discussed, things for homophily, right? Do they share the same characteristic or not? So it gives simple match, no match, count them up, put a term in the model. We could also, so I went through very quickly the homogeneity assumptions, but the idea is the simplest version of homophily would just be match, no match. But we could also do something a little more complicated. We could say, okay, yes, people in the same grade are more likely to interact, but maybe that's true, especially true of people in, I don't know, 12th grade or what have you. And so we could allow for the fact that some in-group ties are much more likely relative to a random network than others. This is especially important when the sizes of the groups are really different. Smaller minority groups end up having generally higher in-group bias. Okay? And so the point is that the models allow you to take that into account. I should have another little box here, but you can also go one step further and have the full mixing matrix. We talked about that at the end of the session yesterday. You can include the full mixing matrix as well. That table, right, that says all the number of times between all the groups. You can include that as well. So you can go from very simple to complex, even within types, even within type to terms. Okay, and as we have talked about earlier, you can also put in terms for the nodal characteristics, both as dummy terms or as if they are continuous. And for example, we could ask, do girls have more or less ties on average than boys? And so these are types of questions we could ask. And again, the way the model is going to work, you're basically asking these questions while conditioning on all the other features of interest. But so far, we're only within the dyad. Only thing that's dependent on is what's going on with the characteristics of I and j. Nothing farther. As we have discussed, you can range out. Sure.
Just half a second. I want to make sure people are following the intuition here, right? So imagine that I have these in-degree, out-degree models are really nice, and I think it's really useful to help thinking about this as your adjacency matrix, right? So if you have nothing in the model, every cell of that adjacency matrix is going to be exactly equal, right? So everyone has the same probability for the density of flipping a coin, ties on and off. But if some people nominate 10 friends and some people nominate 2 friends, the person who nominates 10 friends, their row of the adjacency matrix should be n divided by 10. The other one should be n, or 10 divided by n. The other one should be 2 divided by n, right? So you start seeing heterogeneity in the probability by the rows based on the out degree. Well, if that person receives 20 ties as opposed to receiving 2 ties, then their column should be 20 divided by n instead of 2 divided by n. And so that's what these in-degree, out-degree terms are doing. If you have something like men, and men tend to have more friends than women, then for all rows that have a man, they should have a slightly higher number of probability than people who have women, and so forth. The problem is you can't do this one variable at a time and make any sense. You have to do it all simultaneously, and that's what these conditionings allow you to do. And so the beauty of these nodal attributes and the dyad attributes is those are dependent on either the row features or the column features or the intersection of the two, and that's what it means to say that it's dyadic independent. The rest of these, what we're getting to the next, it's not just a row or column intersection, it's a row or column and some third column intersection, right? And that's when it gets exceedingly complicated. Is that okay, Jeff?
Good.
Jump in there?
Yeah, I'll just add that with the nodal characteristics, specifically with directed networks, you know, what's nice is that you can differentiate between out degree and in degree. So very nice that, so for directed networks, you can, if boys send lots of ties, and that may, so boys send more ties than girls, combined homophily may explain the larger number of, the higher in degree for boys as well, right? And so these are sort of logical things that you may think happen, but the models make it very easy to actually take that into account. And we'll see that when we actually go through some examples in R, but that's excellent. Okay, so good. So as hinted at already, these terms, you know, these terms only are dependent on what's going on within the dyad, what's going on with the characteristics of I and J, or the edge from J to I. Now, we'll very quickly just discuss the possibilities of sort of ranging out a little farther. And so, what does it mean to range out a little farther? It means, you know, if you were trying to predict the edge between, whether there's a tie between going from I to J, what is that dependent on? Well, it may be depending on what's going on outside. You know, not just, so far we focus on things, just the characteristics of I and J, and just the tie from I to J and J to I, just within that. But imagine we think friends of a friend should be a friend, right? So in order to know if there's a tie from I to J, we may want to know, is I and K a friend? If so, and if J and K is a friend, we may think this is much, much more likely than if this did not exist. And so conceptually what's happening is that we are now taking into account what is going on essentially with third-party members, right? Not just the characteristics of I and J, but now we have this person K who sort of factors in and is going to affect whether or not we think it's likely that there's a tie going from I to J. And in general, right, our intuition is that if they have a third person that they both know, they're more likely to themselves be friends. Okay, and so that's question.
Yeah. So I'm thinking about this mostly in terms of egocentric
Okay.
kind of analysis, and I've heard that these graphs are the most common solution, like the preferred solution, when you have alters that span across different ego networks, as well as when the alters are basically shared by egos. I was just wondering if you had heard that, or like what the explanation was, because I don't quite understand.
Yeah, I'm not quite sure what the context is specifically. So within the context of exponential random graph models and ego network data.
Sorry, that's really specific.
No. I would say it is you'd be very careful. Very careful of what you can get out of ego network data with this type of stuff, because with ego network data, you don't actually know very far out into the network, and so you really only have the density, and so the things you can actually estimate are quite limited, if that makes sense.
Yeah, and maybe might be using it differently. So I'm thinking
Okay.
about situations where it's maybe not strictly ego-centric, but it's you do egos and then you do the first wave of alters, right?
Yeah. Okay.
I'll talk to you.
Yeah, we'll chat
Yeah.
afterwards. But okay, so for lack of time, because we are running fairly short. Let me do estimation in like 3 minutes. I don't know. So the point here is that we've now ventured into a world where we are considering what's going on beyond the dyad. We can complicate this even farther by taking into account not just sort of K, but now even more complicated versions of this type of idea. And so this is sort of a triangle. We can also take into account 2 stars, things like that. Another version of this, more complicated, are these, let's say moving beyond Markov neighborhoods, are these shared partner terms. which are increasingly popular for various reasons. The idea here is that imagine we cared about whether or not there's a tie here, right? So imagine we cared about the bottom pair. We want to know is I, so I don't have a label, but imagine this is I, this is J. We want to know is I going to send a tie to J? Well, we may think, look, what's crucial is that they're embedded in the same, this is the way I think about it. I've seen these interpreted in various ways, but the way I like to think about these terms is that if a tie becomes more likely if they end up basically being part of the same social group, and people are going to be part of the same social group if they, in this case, have lots of shared partners. So in this case, this person and this person are both connected to, in this case, two people. It's not just, here we just focus on a number of times. This happens, this actually counts, right? Actually counts the number of partners that pair have in common. And the idea is that the more partners that they have in common, the more likely a tie is to exist. And so the way I interpret this is that the more partners you have in common, the more likely you are part of the same social world, which means you probably know each other. And so these terms basically rely on this type of accounting. So you're obviously going beyond the characteristics of IJ. In fact, you're going out farther and farther into the network. And there are different versions of this term. We'll see when we actually run this in R. So one version is to put in the actual full distribution. What is the distribution of counts of the number of shared partners? This is more common. It's this kind of complicated, geometrically weighted, edgewise shared partner distribution. This is basically a summation of the full distribution. It's complicated, which is why. Well, I'll say this. It's common to see it. Why? Because it fits. It fits. The models fit better with it. And I think that makes sense because it is capturing this idea that people who know lots of the same people are more likely to be tied together. The sort of caveat, is it easily interpretable? The answer is no. Okay. Yes, it is. I think the way it's parameterized is extremely difficult to actually interpret the coefficient, but it is quite common, and they are more stable somewhat, and they do lead to better fits. Okay, so here's list of typical terms. Yeah.
Sorry, just a quick intuition on the geometrically weighted edgewise shared partner. The idea is that, as Jeff pointed out, is the probability of a tie between us is higher the more friends we have in common, but it's not a constant return. If we have 10 friends in common, that gives us a certain effect. The 11th friend doesn't matter as much as the second friend, and the 100th friend certainly doesn't matter as much as the third friend, right? So the fact that we have what the geometric weighting does is it downweights these high levels. Essentially, you can think of it a little bit like thinking something like it's the log of the number of people we have, or some other function of that. The thing that makes it complicated is that there's under the hood there are two parameters. So it's not taking like a simple log or a simple fixed geometric weighting. It's estimating the best marginal decreasing return over time that fits the model. So this is what makes them exceedingly difficult to interpret, but they also don't explode, which is what makes them nice.
Yes. Oh, go ahead.
Sorry, just to clarify, on the last slide, you have you call the geometrically weighted edgewise shared partners a higher ordered term, and my intuition had been that fit into the dyadic dependence models.
Yeah.
And not the higher order dependence models. So is that? Am I reading too much into that? Probably.
Yeah, they are certainly dyadic dependent, right? So they're for sure. So you certainly they are, yes. So they're beyond dyadic independent models for sure. Yes.
Because the way that I've been thinking about this was basically when you're looking at dyadic independence models, what you're looking at are precursors to transitivity, and then when you're looking at dependence models, you're looking at in specific indicators of transitivity because you're saying, okay, we know that social action is happening outside of the dyad, right? Outside of this connection, that things are not dependent. It actually matters, if I'm connected to Albert and Albert's connected to Miranda. Right? Is that?
Right. So these GWESP terms are a more palatable parameterization of transitivity. So it's a way of essentially having triangle terms in there, but without actually having the models actually being able to convert. So yes, I think your intuition is right. I'm not quite sure the specific conceptualization, but yes, it's certainly dyadic dependent. Exactly right. We're going beyond. We're trying to capture the sort of local clustering beyond the dyad. Exactly. That's exactly right. But okay, so let's see. So we have, what time does this session actually end? Because
you have both this section and the
okay.
estimation section, so I think you're set. Does somebody have the schedule cut on? I don't have it.
Okay. Well, let me.
So you're stealing from your own lab. So.
Oh no. Okay. Well, let me.
Maybe do walk through that example. I think it's useful for people to at least see what these things look like.
Yes.
Before we get tried, yeah.
Okay. So let me show you. So what the output's going to actually look like. I'll go through the estimation very quickly because I think running through the actual lab is going to solidify some of the things that we've talked about. But I think seeing it is going to be easier than me trying to talk about it. But okay, so what is the output? What does the output look like? Well, you're going to, in this case, you're going to put a model on, in this case, edges, a number of ties. We also have a node match on grade and node match on race, allowing, so diff equals true is allowing different terms for each grade. We can see we have the coefficients, right? This is going to be the log odds, telling us how much relative to a network of that, a random network of that size, do we expect the number of ties within grade, and allowing it to vary from 7th, 8th, 9th, etc. And we can see in general positive coefficients, right? So that tells us that yes, in fact, there is homophily in the network, that ties between people who match on grade are more likely. And this is especially true in this case, looks like, for people with two people in the same 12th grade. That's an especially likely relative to random network of that size. But you can see the output, has the standard errors and p-values and stuff like that. Physics, SPIC, and ASE. So it has the feeling, right? It has the feeling of something that you may run in Stata and like logistic regression, and so it has much of the same feel about it. Although the actual estimation ends up being much more complicated. Okay. Yes. Oh. So let's hold off on that. So so in terms of interpretation, we'll actually walk through it when we do the lab. So yes, it's coming. Don't worry. We will actually walk through that. How to estimating a model, interpreting the coefficients in the course of the actual lab. But yes, question. Yes. So the answer is going to it's going to depend. If you have a term where imagine a homophily term on, I don't know, hair color or something. If you collected it and it didn't matter, then it ought not to actually be important, right? So there's nothing you could collect data on toenail length. I don't know. You probably don't want to, but you could. And I guess you could ask if the people have the same toenail length, and if it's not going to be an important salient characteristic, then there's no reason to think you'd find a significant coefficient on homophily, right? So no, there's nothing inherent that says you're going to always find significant coefficients. If the process by which you have put in the term isn't actually important in terms of predicting ties, then no, it won't do very much. So the question of nodal characteristics. So if there are big differences between the degree in or out of the groups that you actually are estimating the homophily terms are, then they could change a little. But so it kind of just depends on how different the mean degree is for the groups of interest. And so there's not sort of it's hard to say. It depends on the exact setting in which it could matter, but it need not, especially if the two groups have very similar in and out degree from the beginning. You could, yeah. In which case, you could estimate essentially, a series of models where you start to build up, and you start with homotopy terms, and you could add in terms for alt and in degree, and you can see how it changes. Yeah, absolutely. So that would be again, this is these models are only as good as the question that you have, and so part of it is asking the model the right question. So if you care about how much propensity to send and receive ties affects homotopy, then you should include those terms, and you should interpret those coefficients with that in mind. So I think that's the right intuition in terms of sort of building a model from base terms up to something higher. Okay.
One term that is almost always significant and not much fun to interpret is the edges term. That's literally a model intercept, right? Sure. And so if you're lower than 50% density in your network, then that model, that coefficient is going to be negative and significant. It's not clear it tells you much. But everything else is exactly a feature of the setting, not a feature of the model.
Okay, so I do want to get to the actual lab, because I think that's going to be more practically useful, and it's going to be easier to see how these things play out in an actual setting. I just want to give us, before we take a short break and then come back, very quick sense of what the estimation routine is doing, in order that we can see what the problems are when there are. And so, as already discussed, the problem is that we can't use a simple maximum likelihood estimation, which we would like to, because we can't actually enumerate this bottom denominator, because as it turns out, in order to actually do that, I'm going to walk through this really fast, we need to know something about what the graph statistics would look like for a given set of parameters across all possible networks, in order to say how likely we would have seen those graph statistics based on the coefficients specified. And so in order to know that, you need to know something about, okay, what would, under a set of coefficients, what would all possible networks actually look like? And that is very difficult, as it turns out. And so instead of enumerating all possible networks under a set of coefficients, we do something slightly different. And this is where the MCMC sampling process comes in. And this is important specifically when we look at in the most practical sense, how are we going to know if our model is interpretable, in the sense that the coefficients are okay, that the model has converged, that we can be confident that our estimates are meaningful? And so the key is really knowing when something hasn't gone well. And so the idea is that you're basically going to use simulation. This is all under the hood, but you're basically going to use simulation to generate a set of networks under a set of parameters to begin with. And you're going to, because you can't enumerate all of them, you're basically going to walk through and sample what would the networks look like if this was a set of coefficients, and you're going to use that generated set of networks as a way of basically approximating, we'll call that approximating, what this denominator actually looks like. And so, for lack of time, because I do want to get into the actual lab, what's important is that the estimation requires simulation in order to actually get the coefficients. Which why is that important? Because if the simulation, in terms of generating these networks as a way of making comparisons, if the simulation process itself doesn't work so well, then you can't get good estimates. Okay. So what does that mean? Practically speaking, that means if you start with a model that is not especially good, or you start with a model that does not reflect even close the true, assuming the model is somewhat complicated, doesn't reflect the true underlying processes that generate the network, funny things can happen because the simulation ends up not going so well. And so we'll see examples of this in the actual lab. But what ends up happening? One possibility is that you get so you're simulating these networks in order to basically create a set of networks that are possible under a given set of coefficients in order to estimate what the best coefficients are that could have generated the true network. What ends up happening sometimes under bad models is that these, the set of simulated networks are just completely unrealistic. It's either a completely empty network or it's a complete network, and you cannot get, as I say here, you cannot get good estimates under such conditions. And this is one of the appeals of the geometrically weighted edgewise shared partner distribution, is that it ends up having somewhat better properties than things like triangles and the like. And so, this is a very, very quick, clearly a very quick description. But the point is, what we're looking for is basically make sure the estimation routine has basically done well enough in terms of generating, a sample of networks that we can be confident in our actual estimates. And so this is again, this is I think the first time I did this lecture was like 4 hours, and so this is a very, very brief overview. But what's important is, practically speaking, is being able to recognize when there are problems when you get the actual R output, which we will talk about very briefly. So this is really just about the first step in recognizing whether things have gone well. Can you even trust the estimates at all? In terms of, are these plausible estimates? Has the model converged in the sense that we think things are good enough that we can trust it? The second question is...
Can I interrupt for just half a second?
Yeah.
Okay, I'm going to steal from your lab now. Go for lunch. But the notion of this degeneracy idea is exactly analogous to the Sudoku problem I mentioned yesterday, right? So the idea is the model's trying to fit to randomly sample from the space of all possible graphs that fit the situation you've given it in your real graph. But it might be that you've written down a model that's practically impossible. So imagine, for example, that I have a network that's all triangles and all closed triangles and all edges. So the only two parameters I put in the model, and I have a density of 0.5 in my network. What it'll do is it'll produce half of the networks that are complete clicks of density 1, half of the networks that are complete empty of density 0, and on average you fit the model you specified, but no single draw from that prior distribution because anything close to the world you live in. And that's because you wrote down a bad model. And the thing that's really hard to appreciate is our intuition that we get from regression, where things move slowly and nicely sort of marginal with respect to parameters. So if I imagine a small change in the number of triangles affects a small change in the density of the network, that's just not true in these kinds of graphs. So we have to learn a lot about what the underlying reality looks like, so we write models that match it correctly. And this is where this notion of West came from. It's like we don't need to think about every triangle mattering as much. In reality, there is a marginal diminishing return to having closed friends. And if we write the model down correctly, we get a much more accurate simulation. And so the problem is that these simulations can run. You're doing a Markov chain of 1 million steps. You're never going to look under the hood for all of it. So we need diagnostic tools to do it. In the early ages of these kinds of models, we never would have seen it. And now we can see it better.
Yeah, let me add to that. That part of the tension when you first start with these models is that, in order to even get good estimates, the model kind of has to be good in order before you even start. So we usually don't think about that. If you're running a normal logistic regression, you estimate the model, it's going to probably converge, and then you see, is the model fit any good? Here you kind of have to have a fairly good starting point in order to even ask if the model fit is any good. And so in some ways you have to have a pretty good theory about what is generating the network right from the beginning. And so that kind of mind frame is tricky, I think, for folks, because it's not usually how we think about fitting models. We think about, okay, you estimate it, you look at the BIC or something at the end. A lot of this is up front. In order to even get something plausible, you have to have a good theory of, or the model has to be very simple, or you have to have a pretty good theory of what's going to actually work. And so you have to be sort of closer to the answer than perhaps you'd like up front. But on the other hand, you'll know if it doesn't go well, which we will we will see shortly. Okay, so last slide, and then we'll, I guess, take are the donuts here? Yes, the donuts are here. Excellent. Food, good enough. Okay, so one more slide. We'll take a short break, and then we'll come back and we'll actually do this in R, and we'll see what it looks like. Okay, so last slide on once you've estimated your already well specified model and it has converged and everything is wonderful, then you can ask, okay, is the model any good in the sense that it actually reproduces the features of the network? And so one way of doing this is to estimate your model. You check first the diagnostics to make sure the model has converged, and then you basically take draws, you simulate networks from the underlying model, and you ask, okay, is the networks that are based from my simulated network, from my simulated model, how close or how far are they to the true or actual characteristics of the network? And so what's important is that we are going to ask about features that are not actually part of the model, okay? So you may put in terms for edges and homophily and reciprocity and, GWESP and what have you. And then you're going to ask, does that model, if you generate networks based on it, does it generate networks with features that look like the true network? And those features are going to be things that are not explicitly part of the model, such as a distance in this case. And you can see in this particular model, not so good. And we'll see how to actually interpret these plots when we actually walk through the lab. But the point is that this is one way of judging model fit, is to ask, if I generate full networks based on my model, are the properties of those generated networks close or not to the true network? Okay, very good. On that note, I think let's take a quick pause, and then we'll come back and we'll start running things in R. I will say the code and the data is all up on Dropbox if you want to follow along. Otherwise, I will run it and you can look at it later. But everything's up on Dropbox if you are interested. Okay, very good.